Mechanics describes forces on objects with mass and how and why these objects move or stay at rest. Newton's three postulated fundamental laws form a complete basis for a discussion of such mechanical phenomena. They are, however, most generally expressed using quantities suited well for the description of linear motion, such as linear velocity v or force vectors F. Although the three fundamental laws by Newton cover rotational motion in principle as well, adapting the parametrization to the very different geometry of rotational motion permits a much more straightforward discussion of the mechanics of rotations. This requires the introduction of different quantities, such as angular velocity, the moment of inertia, and torque. This presentation discusses these rotational quantities and combines them to express Newton's three fundamental laws in the context of rotational motion. Let us discuss rotational motion. We want to consider a ball, a tennis ball on a string that circulates about the center on a circular orbit in the vertical plane. Circular orbit in the vertical plane. So we're looking at it. So at the top it may be here, it may have a horizontal position, and it may have a position at the bottom. I have here a tennis ball with a mass m supported by a piece of string, and I can swing it about in a horizontal plane, so that we have in that plane uniform circular motion. The ball is kept on its trajectory by a centripetal force. It's accelerated towards the center of the motion. So its speed does not change, but its direction does. It's uniform circular motion. Hang on, if we now do this in the vertical plane, like this, is this still uniform circular motion? Or does gravity play a role? Gravity always points down. Therefore, it will accelerate the ball on the way down and decelerate the ball on the way up. So at the top, the ball will be slow. At the bottom, the ball will be fast. So we have a non-uniform circular motion with acceleration and deceleration. So, do we have uniform circular motion? That's the question we might ask. Well, the answer is no, because the ball will be faster at the bottom because it's been accelerated by gravity along here. Then it decelerates on the way up and further decelerates, and it'll be rather slow at the top. So we have a slow tennis ball up here and a fast tennis ball down there. So there must be acceleration and there must be deceleration. Acceleration on the way down due to gravity, and then again deceleration due to gravity on the way up. In addition, of course, in order to keep the ball on this circular orbit, we need a centripetal force. So we have the centripetal force, which is provided by the tension of the string and we have gravity acting on it, but only a component of gravity, because at this point the weight of the ball is mg, and some component of this reduces the tension in the string because it acts in the radial direction. So we have a radial component like this of the weight of the gravity force, and we have a tangential component like this which opposes the motion and therefore decelerates the ball, which is on its way to its lowest point up here. And it is only this tangential component of gravity that accelerates and decelerates the tennis ball. A nice example of this type of motion of a mass on a string in the vertical plane is demonstrated by poi dancing, which is quite typical for Pacific cultures. What is the acceleration that acts tangentially on the tennis ball? In order to work this out, and in fact you can look this up in the textbook, Survey Jewett Wilson, example 5.12. In order to work this out, we need to draw a neat diagram of the circling ball and indicate the forces that are acting on it. Let's make this our origin. I'm tracing two axes through it, and as neat as I can, a trajectory, an orbit for our tennis ball, which might at the moment be at this position, and it's held by the string in position. Of course, the tennis ball has a mass m, and on that mass m we have acting at this point the gravitational force mg pointing downward. It's tangential on the orbit, and that's the one that gives us the acceleration at the moment towards the fastest point at the bottom, and then further up it's the deceleration that slows it down to the top. And that tangential component of the weight can be worked out if we can relate this angle theta to the directions of the two components. If we look at this, we have this line, and parallel with that line is that line, and we also have the gravity vector parallel to the vertical, so therefore this angle is also theta. We have a right angle here, and this vector, this length on that length, is equal to sine theta. So the tangential component of the force, which provides the acceleration, and we might denote this as F parallel, F tangential magnitude, is equal to m times g times sine theta. If we rearrange, we find that the tangential acceleration in magnitude is always equal to g times sine theta. Now, what is then the tension in the string? What is the tension in this string? That will vary as well, because the weight will add to it, and the weight will reduce the tension. At the top it will reduce the tension, at the bottom it will add to the tension. This diagram from the textbook nicely illustrates the forces that are acting on the ball for three different positions. Here we have the bottom position, we have gravity acting downward, and it is compensated by the tension force upward that acts as the centripetal force, and the ball moves to the right with a velocity v at the bottom. Then we decelerating the ball to the top where it is slow, and we have a velocity v top now pointing to the left, and here gravity still has the same force, the same magnitude, acts in the same direction and has the same magnitude as at the bottom, but you can see that the tension now is reduced, and it's pointing downward, and the tension can be reduced because the sum of this force, of the tension force and gravity, is sufficient to provide the necessary centripetal force. Then we going downward, accelerate to this point, and now you can see the tension force points to 1 o'clock, and it's rather large again, and the magnitude of gravity of course is unchanged, again points downward, and it is also shown how it can be split into the two components, the radial component mg cosine theta, theta is the displacement angle, and the tangential component mg sine theta, which provides acceleration and deceleration. So the centripetal force mv squared divided by L is provided by both tension and weight, or better, a component of the weight. Mathematically, we have the tension providing centripetal force, and either we adding weight or we subtracting weight, a component of weight, which we just worked out earlier as mg cosine theta. We can arrange this and obtain for the tension T is equal to mv squared divided by L, and it is subtracted by the weight at the top, and at the bottom we're adding the weight in to the tension, and so we have to plus or minus mg cosine theta. We can pull out the m and obtain m times bracket v squared over L minus plus g cosine of theta. So we can see now mathematically that we have low tension at top. That's where the ball is slow ball, and we have low tension, and we have large tension at the bottom. Large tension at the bottom, where we worked out that the ball is fast. We know the ball is fast at the bottom and it's slow at the top. Can we work out how this speed changes? How much faster does it become at the bottom, and how much does it slow down when it goes up to the top? So let's ask ourselves the question, what is the speed at the top and bottom of the orbit? If we know the horizontal position, the speed in the horizontal position, which we might call v0. This is our orbit once more. Then we might know the speed at the horizontal position. It increases, so I have to draw a longer vector at the bottom, and we might call this bottom speed ub. And then on the way up again we slow down, but we're going at the horizontal position, which is our reference to the known v0. And then we have a shorter vector at the top. I made this one too long. A shorter vector u top at the top, and so on. So we could do this kinematically, however it's much more convenient to consider the energies and the work that is performed on the ball. There are two forces, as we discussed earlier, that acting on the ball: tension and gravity. Tension always acts radially on the ball, and since work is defined as the integral of force along a distance, and we have a scalar product in between. If we have 90 degrees between motion and force, we get zero work. So tension does not produce any work on the ball. We don't need to consider the tension force. Gravity, however, always has a component, as we discussed, that is tangential, and that component performs work on the ball. It converts kinetic energy into potential energy into kinetic energy, more potential energy into kinetic energy. So need to consider the mutual conversion of kinetic energy into potential energy and vice versa. Now, if we start our consideration at our zero line, where we might define a potential of zero, potential energy zero, then the energy that has to be conserved, so we're applying energy conservation, that total energy is entirely given by 1/2 mv0 square, because by definition our potential energy at this point is zero. If we then go up, we have a different kinetic energy, 1/2 mu top squared, and we now also have potential energy because the ball is up some height, which is equal to L. So we have to add m times g times the height L at this point, and if we then go all the way down, we have the same situation, only now we subtract potential energy because the ball has less potential energy, so it's minus mgl, and we have a different speed, we have ub. So we get at the bottom 1/2 mub squared minus mgl. So this is the top situation, this is the bottom situation, and this is in the middle, the horizontal position. Now we can divide by m. M is everywhere. We can remove the m and we can rearrange so that the 2 disappears here, the 1/2s disappear, and that gives us the following equation. So we rearrange, and in fact we can obtain 2 equations, one for the top speed here up there, which is equal to v0 square minus 2gl. This 2 comes from the half here, and we can have a similar equation for the bottom speed, which is equal to v0 square, so the square of the bottom speed is equal to v0 square plus 2gl. We rearrange once more and we obtain for the top speed the square root of v0 square minus 2gl, and we obtain for the bottom speed the square root of v0, the known v0 square plus 2gl. You can see there's an interesting conclusion we can draw here. The square root cannot be negative, it's not defined, but if this term 2gl is larger than v0 square, then we have a root of a negative number. What does that mean in physics terms? It means that in order to have an orbital motion, in order to keep that ball, that tennis ball, on an orbit, on a circular orbit, the speed in the horizontal position has to have a finite size which is larger than, in fact the square of it has to be larger than, the square of v0 has to be larger than 2gl. That is required in order to have an orbital motion that is circular and complete. Now for an actual system, we might assume that the speed in the horizontal position, v0, is 5 meters per second, and the length of the string is 75 centimeters. With those numbers, we find, if we write them down first, L, the length of the string, 0.75 meters, 75 centimeters, and a v0 speed of 5 meters per second. The first thing we can do is apply our check. Is that actually possible? We concluded a moment ago that 2GL, which in this case is 0.75 meters times 2 times G, let's assume G is 10 meters per second squared for this estimate, then 2 times that is 20 meters per second squared, and we obtain 15 meters squared on second squared, and that is smaller than v0 squared, which is 5 times 5, 25 meters squared on second squared. So for these initial parameters of 0.75 meters and the speed of 5 meters per second, we can indeed expect that the tennis ball will be on a circular orbit. If we then substitute into these two equations for ut and ub, u subscript t and u subscript b, we get that the square root of 5 squared times the unit m squared over s squared, now minus 14.72 meters squared on s squared. Here I've used g equal to 9.81 meters per second squared, and by working out the square root we find that that's equal to 3.2 meters per second. So at the top the ball has slowed down from 5 meters per second in the horizontal position to only 3.2 meters per second. Now at the bottom, that's about 30-40% slowdown. And at the bottom, UB, if we substitute with those numbers, again, square root of 5 meters squared on second squared, 5 squared meters squared on second squared, and now the same result here, but now we're adding it in, plus 14.72 meters squared on second squared. Add this together, take the square root, we obtain 6.3 meters per second. So you can see now we have accelerated from 5 to 6.3 meters per second. So we have an increase of 1.3 meters per second, and here we have a decrease of 1.8 meters per second. So you see it's not linear. The change is change in speed is not equal. Why is it not equal? Well, we're converting the same amount of energy from the horizontal position as we go to the top as we do when we go from the horizontal position to the bottom. That's the same amount of energy, but speed goes into kinetic energy as the square, and because of that square or the square root of the kinetic energy, then the equal amount of energy on both ways, up and down, translates into different changes in speed. Let's look at the vertical circular motion in a different way and describe it in terms of displacement angle, which might be drawn with respect to this reference line here. This is our ball, and we can define a displacement angle theta with respect to our reference line. Because our motion is non-uniform, we have non-uniform circular motion. This means that theta will increase. This might be theta 2 prime, theta prime. Theta will increase, but the rate of increase for theta, the displacement angle, is also non-uniform. Let's define this rate of increase and call it omega. Omega is the change of displacement angle theta with time, d theta dt. Omega varies with time. What is the meaning of omega? There's some interesting information in omega. Let us ask ourselves that question. What is omega? What is the physics meaning of omega? Well, we can see that for one entire revolution, going around all the way, one entire revolution, we find that the omega, the rate of increase of the displacement angle theta, is equal to 2 pi for one revolution divided by the time it takes to get around, which we may call capital T, and call it period, the period of the revolution, with a unit of radians on second, whereby, I remind you, radians is an indicator, whereby indicating that we're measuring the angle in the natural unit radians and not in degree, whereby S is a unit indicator which has the dimension of 1, and the unit S has the dimension of second. So we have omega, the rate of increase of the displacement angle theta, for one revolution is equal to 2 pi divided by t. Well, that doesn't really tell us much more than we already knew, but if we now divide by 2 pi, we find that omega divided by 2 pi, which we may call f just to simplify, is equal to 1 on t, and that tells us we have 1 revolution per period, and a quantity like that we understand as a frequency. F is a frequency. So omega conveys the meaning of a frequency, although it's not expressed in units of 1 per second, but in units of radians per second. And we need to distinguish this frequency from the frequency f, so therefore we call omega the angular frequency, to distinguish it from frequency f, because they differ by this factor 2 pi. Omega is equal to 2 pi f, a very important relationship. Angular frequency. Now, if the angular frequency is large, we have many rotations per time unit. If the angular frequency is low, we have few revolutions per time unit. So that means this has also got the meaning of a speed, of an angular speed. So sometimes we refer to omega as an angular speed, because that's also information that's conveyed by this unit. Now, so far I've treated omega as a scalar. Is omega, the Greek letter omega, the angular speed, indeed a scalar, or is it a vector? Let's try and understand that question. It is important to note that when we talk about angular frequency, we always have a reference axis. Pointing out of the plane of revolution. And that omega we're talking about is a rotation about this axis. Now, we might define a somewhat weird situation where we have a particle rotating, but the reference axis is in plane. So we might get one revolution, but with respect to this axis, we don't have any speed because it hasn't gone about that axis at all. So in this case, no revolution about the reference axis. So you can see that there is a directional quality associated with omega, and that's why omega needs to be a vector. So omega, the angular speed, is in fact an angular velocity, whereby velocity instead of speed indicates that it has directional quality, and angular is important because it distinguishes omega from f, the frequency, and tells us that omega as a frequency is measured in radians. So omega is an angular velocity and it is a vector. Now if it is a vector, it can point upward to indicate the axis of rotation, or it can point downward to indicate the direction of omega, still being in line with the axis of rotation. So which is which, and how do we understand this ambiguity? Well, we can move in an anti-clockwise sense, or we can move in a clockwise sense. And therefore, it is sensible to define the direction omega as an indicator of the sense of the revolution. And that could be either way around. We could have up anti-clockwise and down clockwise. However, the convention follows the right-hand system, the right-handed system. And that means looking at the motion, an anti-clockwise rotation means omega points out of the plane, and a clockwise rotation means omega points into the plane. This can also be easily remembered thinking about the right-hand screw rule. If you turn a screw into a material, you're turning to the right from your perspective, and that means the screw goes into the material. So the motion of the screw indicates the direction of the vector, and the motion of your hand going to the right indicates the direction of revolution. So this is the right-handed sense, and that represents, and this is the rule, the aid memoir, which helps you possibly remember the direction of omega. This cartoon describes the same convention in a different way. The fingers of the right hand indicate the sense of rotation of the wheel, and the thumb of the right hand indicates the direction of the angular velocity vector. Let us return to our discussion of the ball circulating in the vertical plane. Because it is accelerated on the way down, it will have a larger angular velocity at the bottom compared to the angular velocity on the top. How can we express this change in angular velocity in terms of rotational kinematics? We can do that by introducing the concept of rotational acceleration. So we note that the ball on a string in the vertical plane, circulating in the vertical plane, has an angular velocity omega, which, as we just found out, is a vector that has a constant direction, namely perpendicular to the plane, perpendicular coming out of this vertical plane, a constant direction, but it has a varying magnitude. The magnitude of omega varies. That allows us to introduce the concept, which, as you'll see in a moment, is very similar to what you already know for linear kinematics, the concept of angular acceleration and deceleration. And as before, the term angular indicates that we're not talking about linear acceleration and deceleration. That's where the mistake is. Deceleration. I'll write it once more. Deceleration. You're familiar with linear acceleration and deceleration, and now we're dealing with a different property, which we call alpha. It is also vectorial, similar to omega, the angular velocity. The angular acceleration is also a vector, and it is defined as the time change of omega, and therefore has the unit of radians per second squared. And if we draw the situation we're dealing with, this is our vertical plane, and the orbiting tennis ball, then we have an omega vector coming out, and towards the bottom, so that is this is the bottom, towards this position we're accelerating the ball, so we're increasing omega, therefore we have an alpha vector, an angular acceleration vector pointing upward, in contrast to the situation at the top here, where we're decelerating the ball. So here omega still points upward, but we have an alpha vector pointing downward, an angular acceleration that points downward. We have already seen that there are some equivalencies between linear motion, which you have been introduced to earlier in this course, and rotational motion, which we are studying now. Let me list those and we discuss them. We have in linear motion the displacement, which has the unit meter, and we might indicate that as s, distance. And if we differentiate displacement s with respect to time, we obtain in linear motion velocity with the unit meters per second. And if we differentiate again with respect to time, we obtain acceleration, meters in units of meters per second squared. Equivalently, we have in rotational angular motion displacement angle, theta, measured in radians, rotational or angular velocity omega, d theta dt, so this is the displacement angle differentiated with respect to time once, and the unit is radians per second, and angular acceleration alpha, which is the first differential with respect to time of omega, or equivalently to linear motion, the second differential with respect to time of the displacement angle theta, in units of radians per second squared. So you can see that the situation is very similar. We have to, if we replace displacement with theta, then everything else is the same, with the exception that we have to replace velocity with angular velocity and acceleration with angular acceleration. The question arises, what if we now go to dynamics? In linear dynamics, we are familiar with force, which is given according to Newton's second law as F equals mass times acceleration. What is the equivalent? What takes the place of this very important dynamics law in rotational motion? What takes the place of force and mass in rotational motion so that we can express Newton's second law in terms of angular or rotational motion? In order to answer this question, let us first understand how the kinematics of linear motion and rotational motion are related. So the question is, what is the relationship between the parameters of linear motion, as we have just listed them, and rotational motion, as we have just listed them? In order to answer that, let us sketch the situation. We have our mass moving with a certain velocity, m, on a circle, processing through an arc associated with an angle theta, and the circle, of course, has a radius of L, of r. Then the length of this arc, L, the arc length, is equal to theta times radius r. And we can express the linear speed as v, the linear speed v is equal to the arc length divided by time, which is equal to theta times r divided by the time associated with this stretch of motion. Now, if we assume uniform motion, circular motion, then we can express that as a full circle, 2 pi times the radius of the circle divided by the period, t, and thereby introduce the angular speed omega. Times r. So now we have the relationship we are after, at least for the case of linear speed and angular speed. V is equal to omega times r. Now, all of them are vectors. All those parameters are vectors and not scalars. V is a vector, omega is a vector, and r is a vector. How do we consider that? Well, we need to consider the directions for the type of motion, anti-clockwise, that I've drawn there. We have the situation that omega points upward from the plane of motion. We have the radius vector pointing radially outward, and the linear velocity vector is in plane, and it has a right angle to r. It also got a right angle to omega, and the three are related by the cross product according to v is equal to omega cross r, and that is the most general expression that relates linear velocity with rotational or angular velocity. In linear kinematics, the kinetic energy is very familiar. It's given by 1/2 inertial mass times v squared, linear velocity squared. Since we've now got a relationship between the linear velocity v and the rotational velocity omega, we should be able to express the kinetic energy of rotational motion. And that's easily achieved by substituting. We substitute for v squared with v equals omega times r, and obtain that that's equal to 1/2 the mass times omega r squared in brackets. And we can rearrange this, and we find that that's equal to 1/2 m times radius squared, which we consider together, times omega squared. So this is the rotational kinetic energy. And you note that in this bracket we now have an interesting quantity which we might call rotational inertia, and give it the name I. Rotational inertia I, which is equal to m times r squared. So that takes account of the fact that if we have a rotational motion, the inertia of the mass will resist that motion. However, that resistance is even larger if the mass is located at a larger radius, and even larger if that mass is located at a larger radius r. So the inertia is larger, and it goes with r squared the further the mass is away from the center of motion. So therefore it's appropriate to call the quantity m times r squared the rotational inertia I. And we then find that we can express the rotational kinetic energy as 1/2 I rotational inertia times omega square. And you can see again we have a relationship which looks very similar to the one we obtain in linear kinematics, only now we have replaced mass with rotational inertia and linear velocity with rotational velocity. Well, you might wonder why this rotational inertia is also often called the rotational moment, the rotational moment of inertia. That comes from mathematics, because in general in mathematics a moment mu n is defined as the integral from minus infinity to plus infinity over a function x to the power of n, that's the same n, times that function fx dx. And in our case we're dealing with the quantity I, a moment I, the rotational moment of inertia, which is equal to the integral of 0 to some r naught over r squared mass depending on r. So you can see we have replaced here the x to the power of n with r to the power of 2. Therefore we have the second moment. So the inertia moment is the second moment of the mass, and the function we're considering here is the mass which depends on distance. That's a different distance to that distance. So the mass can be located at a different distance, and we're integrating over that. So that's where this terminology moment comes from the mathematical definition of moment. So we have introduced the rotational moment of inertia. I've shifted here the particle outward, and you can see from the equation that the moment of inertia depends on the distance from the center of rotation. Therefore one might also ask, what happens if we have two particles? What happens if we have two or more mass particles orbiting a center of rotation? Well, they're both adding inertia, so the simple answer is, let's first write down the kinetic energy. The kinetic energy is now the kinetic energy associated with the first particle, which has the moment of inertia I1, plus that of the second particles times omega squared. And we can write this down by substituting for mi. So we have m1r1 squared plus m2r2 squared times omega squared. And the sum in brackets is now the total moment of inertia of both particles. So you can see that moments of inertia are additive, and we can write in general that any total moment of inertia is made up of all the contributions associated with different particles, mi, which are different radii ri from the center, and that radius goes in square, and we're summing over all of them I equals 1 to n, which is whereby n is the number of particles. And that's, by the way, the equation you find in the textbook as equation 922. So the further the mass, the further the mass is away from the center of rotation, from the center of rotation, the more it contributes to the rotational inertia. So if this is my center of rotation and I have a certain mass here, and the mass is circulating about the center of rotation, if I move it out, it will contribute more inertia, and if I move it out further, it will contribute even more inertia, in that way resisting the motion. So since we now can add many mass particles and consider their contributions to the moment of inertia, one might also consider what happens if we have an entire disk rotating about a center of motion. Like this, the entire disk moves anti-clockwise, and we can now identify little masses, delta mi on that disk, and they're all contributing inertia. So this one, for example, contributes in inertia ii, which is equal to delta mi times the radius ri squared, whereby that radius is exactly that distance, ri. And in order to get the total moment of inertia, we have to integrate, and well, first we might add, and then the sum becomes an integration. So I total is equal to the limit of this mass contribution delta mi becoming smaller and smaller, and while we're making them smaller, we're adding them all up by considering also the radial distance ri squared. And if we then, so that is the total moment of inertia for any type of mass distribution. If we now assume a uniform distribution, for example a disk like that, with that rotates about its center, then we can take advantage of the uniform density and express dmi as the differential mass as the density, that's the density, the mass density, times a volume element. So for example, I can take this little volume element here, dV, and multiply it with the uniform density, and then I get the mass differential dmi that is present in that little volume element. And if I substitute here and replace the sum with an integral, I find that my total inertia is now given as the integral over the entire volume V0 of rho times r squared times dV. That is equation in the textbook SJWW, equation 23. And that it can be applied to any kind of uniform mass distribution. And I've already mentioned the disk here. For a disk like that, a disk of finite thickness, or a cylinder for that matter, one obtains a total moment of inertia, which is given by 1/2 the mass of that cylinder by its radius squared. That looks rather similar to the most general equation for moment of inertia, but working this out for a rod, that rotates like this about an axis through its center gives a somewhat different result. For a rod we get 1/12 m times length squared, so you can see that it's not always 1/2. In this case it's 1/12, but again we're dealing with the total mass, and the L refers to the entire length of the rod. And these results and more measurements of more equations for the total moment of inertia are given in table 9.2 of the textbook. So you can look this up in table 9.2 in the textbook. This is the compilation of moments of inertia from the textbook, and you can see some interesting differences. For example, here for the hoop or the thin cylindrical shell, we have a moment of inertia of mr squared, whereas for the cylinder of the same mass we only have half of that moment of inertia, which illustrates nicely that mass as far out as possible contributes more to the moment of inertia than mass further inside. You can also compare the long thin rod rotating about an axis through its center, which has a moment of inertia of 1/12 m times the length squared. However, the same rod now rotating about an axis through its end has a much larger moment of inertia of 1/3, 1/3 of the same mass times L squared product. For a sphere and a spherical thin shell, you have a similar situation. Again, the sphere of the mass m has a smaller moment of inertia, 2/5, than the same mass distributed over just a thin spherical outside shell. And in that case we have 2/3 of mr squared for the moment of inertia. This is a demonstration of the difference in moment of inertia. You've got here two cylinders of equal inertial mass. However, the right one, the metal cylinder, has all the mass distributed about the edge, and therefore it has the larger moment of inertia. Which will therefore roll down a ramp faster? Well, we would expect this one. This one's got the lower moment of inertia. Let's see if that really happens. Here we go. This one is solid and this one is hollow, and indeed the wooden cylinder rolls down the ramp faster. We have seen that the structure of the equations and the parameters we can use in rotational kinematics are very similar to those we already know from linear motion kinematics. For example, we can replace linear speed with rotational angular speed. We have found that the rotational moment of inertia takes the place of inertial mass. However, we have not answered our original starting point, our original question: what takes the place of force in rotational dynamics? Let us come back to our example. The ball circulating in the vertical plane, where we have acceleration and deceleration. So we don't have uniform circular motion, but accelerated uniform motion. In order to simplify the situation, let's assume we accelerate the ball in a continuous way. So we talk about circular but accelerated motion, and not just accelerated in the centripetal direction, but tangentially. So the ball will pick up speed as we continue to accelerate. And we know that in this case we always have a centripetal force keeping the mass on its circular track. But now, in addition to that, we also want to consider a tangential acceleration A, and therefore associated with that a tangential force F. The total force on this mass m, circulating in an accelerating fashion about the center of rotation, can then be written as Newton's second postulate, F equals the mass times its acceleration. And we can express acceleration as the time differential of velocity, and then do a transition to rotational parameters. So we substitute v, we replace v, the velocity, with its rotation equivalent, and can write m times the time differential of the bracket of omega cross r. And now we have partly rotational parameters. We still have the mass from linear kinematics, but we have rotational parameters here. If we now carry out the differentiations, we have to apply the product rule, and we get two parts to it. We get the time differential of dt of omega cross r, plus the other part, which is omega cross the time change of the radius vector. And we know that this radius vector doesn't change in magnitude, but it changes all the time its direction, and that's due to the centripetal force. So the second part represents the centripetal force, and therefore the first part has to be the tangential acceleration that we're after. So we might for the moment ignore this second part and rewrite the tangential force as mass times d dt of omega cross product with the radius vector r. Now let's also replace the mass with its equivalent in rotational kinematics, and that is the rotational moment of inertia. In general, we have I, rotational moment of inertia, as m times r squared, which can be rearranged to give m is equal to I divided by r squared. If we substitute, we find I divided by r squared times time differential of omega cross product with the radius vector. Okay, now let's do something unexpected and see what happens, because we now have rotational parameters on the right. We've got radius, which we can accept, we've got omega, and we have the moment of inertia. All of those parameters are suitable in the description of rotational kinematics, but on the left hand side we still have the force. We're still dealing with this tangential force, and we want to find something that can replace it and has the character of a rotational motion. So let's do something maybe unexpected. Multiply both sides with the radius vector cross. We have to be careful. You know from mathematics that the cross product is not commutable, so we can't swap the parameters, so we multiply from the left cross product to the right on both sides. That gives us r vectorial cross f tangential is equal to the mass we can pull out times r cross product of d dt omega, which we can also now replace with the rotational acceleration alpha cross r. Let's rewrite that again, including the alpha, and we obtain m of, I've already replaced m, so the m should really be I divided by r squared. I divided by r squared times R cross product with rotational acceleration cross product with R. So now you can see that on the left hand side we have a term which we might give a new name. We call it tau and torque. And on the right hand side we have the magnitude of R squared, and we have the magnitude of R once and twice. So this in fact cancels out to give us I times the radial unit vector cross A cross the radial unit vector again. So we obtain tau for torque is equal to a moment of inertia times E unit vector in the radial direction cross alpha, the rotational acceleration cross again unit vector in the radial direction. What is this? Well, the easiest way to understand that is to draw the situation. So we have the unit vector in radial direction, ER, and we have a cross product with the acceleration which is pointing upward from the rotational plane, and that gives us a vector that is EA, that's pointing in fact into the negative tangential direction. ER alpha, right hand rule, pointing in the negative. So that gives us this vector. So this vector is ER cross alpha. And now we multiply this vector again with ER in the right hand sense, and that gives us a vector pointing upward. And since ER and ER have the magnitude of unity, this vector has the magnitude of alpha. So all we're getting back out of this is alpha. So this is alpha. You can also see that this is a geometric way of looking at it, vector algebra way of looking at it. You can also see this algebraically if you apply the Grossman rule, which says that if you have ER cross product alpha cross product ER, then that's the same as writing alpha times ER dot product ER minus ER and then ER with dot product with alpha. And a dot product between two identical vectors, unit vector gives 1, and these two vectors, the radial vector and alpha, are perpendicular to each other, so therefore this gives us 0, and again we find that this term gives us alpha. So after this little excursion into vector algebra, we can then conclude that our new quantity tau, torque, is equal to moment of inertia times rotational acceleration. Rotational acceleration. And here we have inertial moment. And you have to agree that that now looks rather similar to Newton's second law. We have a new quantity torque replacing the force from linear dynamics. Inertia replaces inertial mass, and instead of linear acceleration we have rotational acceleration. So this is the equation we were after. This is Newton's second law in rotational parametrization. and you find it in the textbook as equation 914 and as equation 920. We have just defined torque mathematically as radial distance cross product with the force that is applied, giving us a rotational torque tau. But what does that mean conceptually? Well, I've brought 3 screwdrivers here, and torque is all about putting this screw into timber. If we take this screw and apply a small screwdriver like that, then you can see we have a small radial distance here, and if we try, it takes quite some effort to get that screw into the timber. If we instead apply this much larger screwdriver, which has a larger radial distance r, you can see now it's much easier for me to turn the screw into the timber. And this is the intermediate situation. We have now a screwdriver that has a smaller radial distance to the point where my thumb applies the force. This is shorter than that, and it will require me now to apply somewhat more force to turn this screw into there. So small screwdriver, very hard. Intermediate screwdriver, somewhat easier. And finally, the large screwdriver with a large radial distance, straightforward. Let's summarize this on paper. So this new quantity we have introduced is called torque, and it has the symbol tau after the Greek, using the Greek letter tau. And I haven't mentioned the units. The units are meters, radial distance times force, so it's meters times kilograms times meters per second squared, or summarized as Newton. So we have kilograms times meter squared on second squared, and that again is equal to Newton meter. Now you might say Newton meter, I've heard that before. That's in fact also the unit of work, but work and torque should not be confused. They are two very different physical properties. That's particularly apparent because of this fact: work is a scalar, whereas torque is a vector. So don't confuse work and torque, despite them having the same unit, Newton meter. We also just illustrated using the screwdrivers that if we have a given torque, then we can produce that with a short radial distance by applying this force F1 at a distance R1. However, if we now move further out to a distance R2, the force we require to achieve the same torque in the same direction and magnitude is smaller. In fact, it only has to be half the force at the distance R2 that is required to achieve the same torque. So longer leverage, one might say, requires less force for the same torque. Following our introduction of the angular speed, the angular velocity omega, and now the torque, you realize that you have to become familiar with the cross product if you not already are. This, you might have not come across that in mathematics, so let me tell you a few of the important aspects of the cross product. If you've got a vector A, this vector A here, and you have a cross product of A cross B, then the resultant vector is the purple vector, which is pointing upward from the plane, or away, perpendicularly away from the plane that is spanned by A and B. And the magnitude of this purple vector A cross B is equal to the product of A times B. The direction has to be in a right-handed sense. If this purple vector would be pointing downward, we had the negative cross product, but it's pointing upward because the definition requires a right-handed sense. And you can remember that by using your right hand, whereby A is pointing, is the pointer, B is the middle finger, and the thumb is then the resultant vector, the purple A cross B vector. Mathematically, you can work out a cross product using the determinant. You can write A cross B as the A vector components in the top row, AX, AY, AZ, underneath the BX, BY, BZ component of the B vector, and that's followed underneath again by the X, Y, Z unit vectors. And the components of the A cross B vector, the purple vector, are then given by this complex term at the bottom here, AYBZ minus BYAZ in the X direction, AZBX minus BZAX in the Y direction, AXBY minus BXAY in the Z direction. If you can't remember that, which many people find hard, you can derive it from the determinant. If you write the vectors like this, the A vector, the B vector, the unit vectors, and the A vector again, the B vector again, and then you can look at the diagonals. If you take this diagonal, for example, you have AZ times BZ, and everything on the right gives you negative components. So you've got the AZBYX component of the resultant vector, and if we take another diagonal, we have BZ times AX is the negative component in the Y direction, and if we take other diagonals to the right here, we have BX times AZ. We get a plus, because we're on the right now, plus AZBX times the Y unit vector. So 1, 2, 3, 4, 5, 6 terms which are contained in this expression are all present as diagonals in this aide-memoire. I've listed here Newton's postulates for linear motion, and with the introduction of torque we are now in a position to write them down for rotational motion as well. All we have to do is change a few words. We have an inertia principle for rotational motion. So for rotational motion, Newton's postulates look like this. The inertia principle becomes, in the absence of an external force, now has to read external torque. In the absence of an external torque, a body is either at rest or in uniform, not linear, but in uniform circular motion. That's the inertia principle for rotational motion, the first Newton postulate. The second Newton postulate, the second Newton law, force is equal to momentum change, reads, an external force causes a momentum change. For constant mass, it follows that F equals m times a. This is now an external torque, force becomes torque, causes a momentum change. Here we have to write an angular momentum change, and you realize that this is a quantity we haven't discussed so far, so this is still missing in our discussion. Angular momentum. What is angular momentum? An external torque causes an angular momentum change. But we can continue and say for constant mass, here we can replace mass with for constant rotational moment of inertia, which we have introduced as I, it follows that not F is equal to m times A, but that torque, which we just talked about, is equal to inertial moment times angular acceleration. So torque takes the place of force, moment of inertia takes the place of mass, and alpha, the angular acceleration, takes the place of the linear acceleration A. That's the second Newton law for rotational motion. And N3, actual equals reactual, reads in the linear version, a force always has an anti-equal reaction force that acts at a different point. Here we now have to say a torque always has an anti-equal reaction torque that acts at a different point. No, it can't. A torque can never act at a point. A torque needs an axis, so here we need to write axis. So Newton 3, actual equals reactual, reads a torque always has an anti-equal reaction torque that acts at a different axis. As in linear dynamics, Newton's postulated laws for rotational motion form a complete basis for any discussion of any type of rotational motion or any type of situation where torques are applied. Let's therefore spend a little bit more time discussing these three very important laws. The inertia principle allows us to go into a discussion of static situations that involve torque. Newton 2, an external torque causes an angular momentum change, allows us to understand what we mean by angular momentum, and we will discuss angular momentum in a moment. And Newton 3, actual equals reactual, needs a little bit more of a motivation, and we'll do that using the example of cogwheels. These two cogwheels illustrate the relevance of Newton's third law of rotation. In order to move in an anticlockwise sense, the bigger cogwheel needs to receive a torque that is left-handed, so it's a negative torque, and it applies this torque here to the smaller cogwheel, which moves in a right-handed sense. So the right-handed motion of the cogwheel is similar to a torque, a right-handed torque about this axis. So we have a left-handed torque about this axis, which is the action torque, and that induces a reaction torque about this axis on the left, which is in a right-handed sense. Newton's first law for linear motion and the equivalent one for rotational motion form together a very important basis for a field of physics, statics. N1 for linear motion, N1 for rotational motion. You can see that any object that fulfills both cannot be in linear motion and circular motion at the same time, so it has to be at rest. That means these two conditions are equivalent to the condition for static equilibrium. Every object that fulfills both Newton 1 linear and Newton 1 rotational is in static equilibrium. This is typically expressed in a different way, namely as the net force and the net torque acting on the center of mass of an object are both zero. That's the condition of static equilibrium. Mathematically, one can put it this way. An object does not undergo translation, therefore the net force on that object has to be equal to zero, and it can also not undergo rotation, so that we can say all the torques have to be equal to zero. The net torque, the sum of all torques, the vector sum of all torques has to be equal to zero. When both of these conditions are fulfilled, then we talk about static equilibrium. Now, a classic example of this situation is that illustrated here and already formulated as a problem. A ladder leaning against a wall. We have a slippery wall, a ladder with possibly a person on it and some weight associated with that. So we have gravity pointing downward. Standing on the ground, but the ground is rough, reasonably rough, because it has to be like that so that the ladder doesn't slip. Because the weight of the ladder and the person on the ladder will induce a torque about this pivot point that tries to move the ladder beyond the wall. However, the wall is sturdy, and therefore there is a normal force compensating for that, the effect of that torque. This normal force, on the other hand, has to be compensated by a friction force on the ground that is at least of equal magnitude. If that friction force is not there, the ladder will slip at this point, and person and load will fall onto the ground and possibly end up in hospital. This model nicely illustrates the ladder problem. We have a ladder leaning against the wall, which is rather slippery. However, it's on rough ground, and we know if we make this angle to the normal small, then the ladder will be stable. But eventually, if we make the angle to the normal here larger and larger and larger, it will slip. And that's because the weight on the ladder, which we might symbolize by Kenny the koala here, Kenny is sitting here on the ladder trying to paint it, and that means there is some additional weight on the ladder, and that weight pointing downward, having a force pointing downward, creates a torque with respect to this pivot point, and the torque presses against the slippery wall. In order to compensate for this torque, there will be a normal force pointing outward, and that normal force needs to be compensated by the friction down here on the ground. So if we make this angle larger, the normal force will become larger, and therefore the friction has to be larger. But friction is limited, so there will be a critical angle and the ladder will slip. The problem becomes even larger if we put some paint cans on there and increase the weight, because the torque pushing against the wall will be larger, the normal force will be larger, and we require an even larger friction force to make the ladder stable. So it will slip at an earlier angle. We can see that quite nicely if we reduce the friction on the ground and create a very slippery situation. You can see at this angle the ladder is still stable, but if I move it out to this point, it now starts slipping and it falls down. This kind of problem can be solved with the condition of static equilibrium. So let's illustrate the situation a bit further. So we have a point B here, a possible pivot point B there, a possible pivot point A there. And in addition, the ladder has a length L, and for the moment we might ignore the person, we just consider the weight of the ladder itself, and that results in the force mg downward. The question is, a ladder is to be placed against a wall standing on a reasonably rough surface. Experience tells us that an angle theta, that's the angle theta here, measured with respect to the normal. Experience tells us that an angle theta, different from 0, should be chosen. Well, if the angle was 0, then it would be a very unstable situation in any case, because you can't put your own weight into the center of mass and the ladder will fall over to the back. So we have to assume, in order to have a non-trivial situation, that theta should be finite, but theta should also not be too large, because otherwise the ladder will slip. And the question, of course, is for what angle theta does the ladder slip? So I've already said that we have a torque about this pivot point, and in response to that we have a normal force pointing outward in this direction, and we might call that F normal, and that then has to be compensated by an equal force in the other direction on the ground, which is the friction force, which we might call FF. How do we solve this problem? Well, let's summarize what we know. So we've got two pivot points, and we know that mg creates a torque about the fulcrum or the pivot point A. In particular also about B, but we're interested in A because A needs to be compensated by the normal force Fn. This effect, the effect of the torque against the wall, is compensated by the normal force Fn, which drives the whole system to the right. So we need some other force that keeps it on the left, if you like, and that force is the friction force. So we can say Fn compensated in turn by the friction force Ff. And the question we want to ask ourselves, why is the ladder stable and is there a critical angle? Well, we know from experience, if we make this angle theta larger, eventually the ladder will slip, and just before that, that will be the critical angle. Now, mathematically, we can solve the problem in this fashion. Let's start out and apply the condition of static equilibrium. And as I told you, there are two. These two, we want to start out with the condition for rotation. No rotation is allowed if we want to require static equilibrium. So about any axis, the sum over all torques has to be required to be 0. So in our case, we might apply that to a vertical axis through A. Apply to the pivot point A. Then we have the following equation. We first write minus Fn times cosine theta times L. That is the torque that is due to the normal force about this pivot point, but we need a component of this. Yeah, we need a component that is perpendicular to the ladder. Let me sketch this situation. So this is our ladder, and the angle theta shows up here, and this is the actual normal force, but the component we want is this one. And that component is equal to, the cosine also shows, the angle theta also shows up here. So therefore this component is equal to Fn times the cosine of that angle, Why do we have the minus sign? The minus sign comes about because we have a torque that is anti-clockwise. Sorry, we have a torque that is clockwise. We have a torque that is clockwise, and therefore by convention the contribution has to be negative because the torque is clockwise. Another contribution to the torque is due to the weight mg. I didn't say why I used L. L of course is required because the distance between the point of the where the normal force attacks and the pivot point A is equal to L. Another force arises because of a component of the weight, which is this component here, and that's given as mg times sine theta, and in this case the distance to the pivot point is L half, so times L half, and now we're turning anti-clockwise, so this component is positive. Furthermore, we might have contributions due to the friction force here. However, the friction force attacks in the pivot point, so that means its contribution is 0. Now that's all the forces that are present and all possible torques we can consider, and because of the condition of static equilibrium they have to be equal to 0, so we can require that that sum is equal to 0. Rearranging this gives us Fn, this normal force, we can isolate this normal force, is equal to 1/2 mg times sine theta divided by cosine theta. Yeah, the sine theta comes from here, cosine theta comes from there. We've simply rearranged that equation. This can also be written as 1/2 mg tangents of theta, and if we draw the geometry once more, this is our ladder, and we now introduce a distance d from the wall and a height h with respect to the wall. Then you can see, and the angle theta is here and there, and you can see that the tangents of theta is equal to d on h, so we can also write this is equal to 1/2 mg d on h. Okay, so now we know the normal force in terms of the geometry, and because of the other condition of static equilibrium, namely that no translation is permitted, the net sum of all forces has to be equal, and that's what we want to apply now. Yeah, so this was the first thing. The rearrangement might be the second step of the solution. In our third step of our solution, we now apply the no translation condition, and that requires that F net has to be 0, and in this case, in the horizontal direction there are two important forces. One is the normal force, the other one is the friction force, and in order for the sum of those to be 0, the normal force in magnitude has to be equal to the friction force in magnitude. We can now substitute in here. This might be the fourth step, trying to get this all onto this one piece of paper. So in the fourth step we're substituting, and we find an answer to our question, how large does this friction force have to be so that the ladder doesn't slip? It has to be at least equal to 1/2 mg tangents theta. And you can now see, if I make this angle theta larger and larger, then the required friction force has to be larger, so eventually there is a critical angle theta for which the friction is not sufficient and the ladder will slip. We just discussed the consequences of Newton's first law as expressed for rotational motion, namely the entire field of statics, which is based on the condition of static equilibrium, which requires that the net sum of all forces and also the net sum of all torques has to be equal to 0 for an object to be stable. Earlier, we discussed Newton's third law as expressed for rotational motion, namely that every torque requires a reaction anti-torque. We haven't completed our second law as expressed for rotations. And this is because we haven't introduced the concept of angular momentum, which is very important in rotational mechanics. One might paraphrase Newton's second law as an external torque causes a change of angular momentum. This is similar to the second law in the case of linear motion, where we talk about an external force causes a change of momentum, linear momentum. We understand what we mean by linear momentum, that's the p vector, but what is angular momentum? What do we mean by that? Let's try to understand that. If we again look at a particle with a mass m circulating about an origin, then it has an angular velocity of omega, and if we accelerate that particle in its right-hand sense motion, then we also have a torque applied here, and that torque may be applied by giving it a push using this external force F. Then we can write this torque. By the way, last night I found out that this is best translated from English into English as twist. So we're giving a twist. When we apply a torque, we're giving a twist. And apparently the word torque was only introduced into language and physics, for that matter, in the last century, well, in the 19th century. So a torque can be written as the radial vector cross product with that external force F. Now, applying the concepts of linear mechanics, Newton's second law in its general form, which you're familiar with, which is force, external force is equal to momentum change. If we substitute with that, we get R cross momentum change, d on dt p. Now, this is a point where it becomes clear that mathematics is the language of physics and has to be the language of physics, because it produces insights which are otherwise not as readily available. And you'll see that in a moment, what we might do now, which we can do mathematically, so this is now stepping back from physics and looking at this equation here mathematically, you can always add a zero. But if you do that, you want to do that with a purpose. So we're adding a clever zero, what I call a clever zero. And I'm not the only person doing that. Every textbook does it, so this is not a subjective thing I'm doing here. This is the way to do it, and we obtain torque is R cross d on dt p, which is what we already had, and now we're adding our zero, and we're expressing it as dr differentiated with respect to t cross p. You might say, well, that's not zero, that's some funny term, but let me show you that this is zero. If we look at our motion, then at some point t1 in time,
we have this radial vector r1, and then we have r2 at a later point in time, and the change of the radial vector is that little difference vector here. So this is the delta r, and you can see that that vector delta r, the change in radius, is equal in direction as this blue vector, which is the momentum vector of our particle. So that means the delta r vector, and therefore also delta r on time, which is equal to v, the velocity vector, is parallel to the momentum vector. So this vector is parallel to that vector, and the cross product between two vectors that are parallel is 0. So this is why this is can be called, or maybe called, a clever zero. Okay, so this is the first input of mathematics, which doesn't involve, well, it involves some physics thought, namely this argument here. But now we do another mathematics argument, because we can see, if we look at that expression on the right hand side carefully, that that is a consequence of the product rule. And in fact, the torque, the product rule of differentiation, in fact the torque is equal to the time differential of r cross p. And since the r vector points out like this, and the p vector is perpendicular to it, we obtain a cross product vector that is perpendicular on this plane, which we can identify as being parallel to the omega and also parallel to the tau vector. And that's interesting, and it's a new vector. It's not omega, it's not tau, it's something else, and because it may be important, we give it a special name, and we give it the name L, and we call that angular momentum. So angular momentum is defined as a vector which is equal to the cross product of the radius vector cross the momentum applied. That's what we want to understand as angular momentum. What importance does this angular momentum vector have? What is the significance of angular momentum? What is the significance? We wouldn't give it a special name if angular momentum L wasn't important. We would just leave it as r cross p. But there's obviously some significance to it, and that significance I want to illustrate now. So let's write again. The definition: angular momentum is defined as r cross p, and we can now substitute for p, remembering what we've learned in linear mechanics. So we get r cross mass times velocity vector, and now we do another mathematics trick. We multiply with a clever 1. Multiply with a clever 1, which is always possible mathematically. Does it have any physics sense? We'll see in a moment. And that clever 1 we express as radius divided by radius, the magnitude of the radius divided by itself, times r vector, that's now coming from here, cross mass times velocity vector. Now if we look at this expression on the right carefully, we can arrange that in a different way, and we get m times r, which considers this r, this m, and the magnitude of that r vector, that gives us that. And we working out that the direction of this vector, the cross product, the direction of this vector, r cross v, has to be perpendicular on this plane. So this this vector has to point in the direction of the EZ direction. So if this is if our coordinate system is x, y, z, or polar with r, theta, z, and then this is the z unit vector. It has the magnitude of 1 and it points upward. That's because r cross v gives us that direction. So far we haven't included this r here and the magnitude of the velocity, the speed. Let's do that now. So we get v on r. And I might complete my color scheme here. So the vectors give us the direction. The v on the blue r gives us that, and the rest gives us m times r. Okay, now if we now interpret this term, we find that m times r squared is nothing else than moment of inertia. And v on r, pointing in the z direction, should be in blue. V is equal to omega cross r. Everything vector has to be green. So we know v is the cross product of omega cross r. So therefore v on r in magnitude is equal to omega. So we have moment of inertia times omega. And the vector needs to be green. So moment of inertia times angular velocity. So the angular momentum is also equal to the product of moment of inertia times angular velocity. And again you can see that this is an analogy to linear mechanics, because there we have P equal to the inertial mass times the linear velocity. Here we have the inertial moment times the angular velocity. In linear mechanics we have mass times linear velocity. Analogy to linear mechanics. Okay, that's very important, a very important result. So not only is the angular momentum equal to radius cross momentum vector, it's also equal to moment of inertia times angular velocity. Let's look at a couple of important special cases. And a very important one, that's our ball moving in the horizontal plane. And in that case we're talking about uniform rotational motion with a constant speed. Well, I shouldn't use speed anymore, I should talk about constant angular momentum. Constant angular velocity, angular speed. Constant speed and constant angular velocity, which might be this vector here. That's what we call uniform rotational motion. And in this case, the angular momentum vector, which I can also draw into the diagram, is different from omega, and it's equal to the moment of inertia of this mass, which is I is equal to mr squared times the omega. And the important consequence of this being uniform motion is that that is constant. So in the case of uniform rotational motion, we have constant angular momentum. That is the very important first special case. So in uniform rotational motion, angular momentum is a conserved quantity. That doesn't mean that the moment of inertia has to be constant and the angular velocity has to be constant. They can vary. However, since the momentum has to stay constant, if the moment of inertia goes up, the angular velocity goes down, and vice versa. If angular velocity goes up, the moment of inertia goes down. This is what ice skaters do. They start with a large moment of inertia, reduce it, and then spin at highest angular velocities. Let us illustrate angular momentum with the example that we have used earlier, ball on a string. If we consider this ball circulating about the origin in the horizontal plane, then we can work out the angular momentum, which is pointing upward and has a magnitude of the cross product R cross P. We can substitute and obtain R, which is the radius. Earlier we assumed a length of 0.75 meters, times momentum is m times v, mass might be 100 grams, 0.1 kilograms, and the speed, we might assume the ball has a speed of 5 meters per second. So if we substitute this, we get 0.75 meters times 0.1 kilogram times 5 meters per second. Let's start that in the calculator. 0.75 times 0.1 times 5. 0.375. 0.375 kilogram times meter squared on second. This example also shows us what the unit is of angular momentum, namely kilogram times meter squared on second. So the dimension is mass times length squared on time. Another related example, if we now turn the horizontal plane into the vertical position. If we consider a vertical plane, then we have in our example with this ball, we now have an acceleration on the way down and a deceleration on the way up due to gravity. This means on the way down, a right-handed torque is applied to the ball to make it go faster, and on the way back, a left-handed torque, now pointing downward into the plane, is applied to decelerate the ball. Nevertheless, we can work out the angular momentum. We can consider three positions. In the horizontal position, as we've done before, we might assume the ball has a speed of 5 meters per second, which is the same on the other side. And we will find that for the horizontal position, we get the same result as just a moment ago. L is equal to 0.375 kilograms per meter squared on second. But what is the angular momentum at the bottom? And what is it at the top? At the bottom, it should be larger because the ball is faster, and at the top, it should be smaller. So L bottom is we have still 0.75 meters, 0.1 kilogram mass, and string lengths don't change, but the speed changes. And earlier we worked out that the speed on the at the bottom, I looked this up, is 6.3 meters per second, and then at the top we have all the same, but the speed is different, and it's 3.2 meters per second. So that means now if we type that into the calculator, we get 0.75 times 0.1 times 6.3, which is 0.473 kilogram meters squared on second at the top position, and at the bottom we get 0.75 times 0.1 times 3.2, which is 0.24 kilograms meters squared on second. The conservation of angular momentum in the absence of external torque in magnitude and in direction is a very important concept in physics, just as important as the conservation of linear momentum. Many demonstrations show that this is indeed the case. What you see here is a gyroscope that has been mounted in a plane, and you can see that the direction of the angular momentum associated with the gyroscope is constant, while the plane moves about. Another interesting demonstration of a constant angular momentum vector is that of a top without external force. A top without external force, a spinning top. Here is a sketch of such a spinning top. And importantly, in contrast to most other spinning tops, in this case the pivot point is in the center of mass, or in the center of gravity, more correctly speaking. If we now spin this, then the top will have an angular momentum component L1. If we then give it a kick like this, there'll be a second angular momentum component L2, and the net angular momentum vector will look like this. And this, without any further external forces, this net angular momentum has to be conserved. And you can see in the demonstration in a moment that the top achieves this by a wobbling motion. And one can observe three axes: the figure axis, which is the symmetry axis of the top itself, the angular momentum axis, the L net angular momentum axis, which of course is constant, and the rotation axis about which the wobbling motion occurs. So we have figure and rotation axis. So in order for this to happen, we have to have a precession motion. The figure axis precesses about the angular momentum vector on one cone, and the rotation axis precesses about the constant angular momentum vector on a different cone. I've got here two tops, a shiny aluminium one and this one made out of plastic. They look very similar, but they are in fact quite different. This one, the green one, is a top with external forces acting on it. You can see that because it falls over. It's not supported in its center of gravity, and therefore gravity acts on it, and if it's at rest, it falls over. If I spin it,
then gravity causes it to precess. And the description of this precession mathematically is quite difficult. Much simpler is the description of this top, which is not affected by gravity. You can see it's supported in its center of gravity, and I can put it therefore in principle in any position I like. It's not tipped over by the force of gravity. It's therefore called a top without external forces. And the physics at play here is the physics of angular momentum conservation. In order to understand this, we have to consider three axes. The symmetry axis of the top itself, which is also called the figure axis, because sometimes you have a little clown or something sitting on top of here defining this figure axis. Then, of course, it rotates, so that there is a rotation axis, and at the moment the rotation axis is aligned with the figure axis pointing upward. And because we only have one component of angular momentum, the angular momentum is also aligned with the figure and the rotation axis. All three axes, figure axis, rotation axis and angular momentum axis, are pointing upward. They are aligned. The situation changes if I supply a second component of angular momentum by giving the top a kick, for example, like this, downward, a downward kick. That means there is an angular momentum component here like this, an angular momentum component provided that turns in a right-handed sense like this, and it's perpendicular on the original one. That means the resultant angular momentum is now not pointing upward, but somewhere like this into space. And because of angular momentum conservation, it has to stay there. It is constantly in space, and we cannot see it. We can just imagine it. We can calculate it because we know the original angular momentum is upward. Then the tip over gives a second component, and the resultant now points this way. However, we can nevertheless see it because the other two axes, the figure axis and the rotation axis, will precede about that angular momentum axis that is fixed in space. Let me demonstrate it. So first, we spin our top without external forces really fast. Then we apply an angular momentum component downward like this, and you can see now we have a wobbling motion, and the angular momentum direction is like this, and you can see the figure axis precesses about that axis. I'll do this once more. Now it's really dramatic. So we've got the angular momentum pointing like this, the figure axis precessing about it, and but where is the rotation axis? The rotation axis we can make out if we look. I'll do it once more. If we look onto this millimeter paper, and you can see I've indicated a few dots, and one of them is really visible. That's the dot which is almost at rest, and at that point we have the rotation axis penetrating through this plane, and you can see that the dot which is visible, there it is now, it also precesses about the angular momentum vector. So we have all three vectors, the angular momentum vector right in the center, the figure axis precessing about it, and the rotation axis precessing about it as well, giving us this wobbling motion. Now you can see it really nicely. One of those spots is almost at rest. That's where the rotation axis penetrates through this plane. It's illustrated here. Well, first of all, the bottom tells us this is a spinning top without external force, and what's shown here is the constant axis of angular momentum, the figure axis precessing about it, and finally the rotation axis here, this axis precessing about it. So this is the precession cone for the figure axis, this is the precession cone for the rotation axis. The angular momentum axis is constant. In this presentation we have only touched on important aspects of rotational motion. The field is much larger and its applications are manifold. The gyroscope demonstration gives a glimpse of the technological importance of rotational motion since effectively every space and aircraft uses gyroscopic technology of one sort or another, while being the subject of a multitude of torques and angular accelerations. However, we have discussed all relevant physics quantities required to express Newton's postulated laws using a parametrization suitable for rotational motion. These quantities are analogues of their linear motion cousins. Here is a nice table from the textbook that shows that analogy between translational motion, as you learned about in the first part of this course, and rotational motion about a fixed axis. We have correlated the angular speed and the angular acceleration to translational speed v and translational acceleration a. We have learned that torque is equivalent to force in linear motion. If angular acceleration is constant, then this set of equations applies, which is equivalent to the ones you know from linear motion. Although we didn't specifically discuss that, but it's apparent that that is the case. We didn't also specifically discuss work, but work is in analogy to linear motion defined as the integral from one displacement to a final displacement angle over the torque times the displacement interval. We mentioned rotational kinetic energy as 1/2 moment of inertia times angular speed squared, which is equivalent to the familiar kinetic energy 1/2 mv squared. We didn't talk about power, but we certainly pointed out that angular momentum, defined as moment of inertia times angular speed, is a very important property of rotational motion, and it's a conserved property just as linear momentum in linear mechanics. So with the introduction of those equivalent rotational parameters, one can formulate the three postulates of Newton in this fashion. The first postulate, the first law by Newton, reads: in the absence of external torque, rotational motion has a constant angular velocity. That's the equivalent of Galileo's Inertia Principle. Newton 2 reads like this: an external torque causes an angular momentum change, and for constant moment of inertia, torque equals the product of inertia moment and angular correlation and angular acceleration. That's the equivalent of the equation F equals ma. And finally, the axial equals reaction principle. Any external torque has a reaction torque partner that typically twists as a torque about a different axis.